Okay. Thanks, Ehud. It's great to be back with the remaining of the time. I'll give some presentation. So yeah, it's great to be back at UC Berkeley. I used to visit regularly when I was in academia, and I'm glad to be back this time. So as Ehud was saying, I work at Google Quantum AI. This is the team in Santa Barbara at the moment where they are building a quantum computer. But the work I want to tell you about today is not from what I did within this team, but my previous work, my first engagement in industry, when I first joined Google X. And it has to do with using Tensor Processing Units as scientific supercomputers. So it's going to be, I find this talk is the one with least scientific content I've ever given. And apparently people like it because you don't go too much into detail. So I want to tell you a story, basically. Let me see how this works. So let me announce the main result is that we were able to repurpose Google's Tensor Processing Units, and I'll tell you what those are in a minute, which were designed for machine learning tasks. We were able to repurpose those for non-machine learning tasks. Okay, we were able to use those supercomputers for tasks such as linear algebra, large-scale dense linear algebra. And an example of things you can do is you take two matrices of size 1,000,000 times 1,000,000, you can multiply them, and in 2 minutes, that was the result. It's 1-year-old result. So in the meantime, probably we can do that. We could do that under a minute now. Don't try to do this with your laptop. If you use your laptop, you can multiply 1,000 matrices that are 1,000 times 1,000, maybe 4,000 times 4,000. If you have a big laptop, a little bit more, but this is 1,000,000 times 1,000,000, which is huge compared to what you would be able to do at home. So we managed to repurpose this hardware to do supercomputing calculations for linear algebra, also for quantum computer simulations, for quantum physics, for quantum chemistry, for tensor networks and finance. And for instance, for quantum chemistry, we managed to get the world's largest computation in something called DFT, Density Functional Theory, using 250,000 orbitals. And if you don't know about this technique, that's fine. But if you know about DFT, you will appreciate that the 250,000 orbitals is like crazy. Okay. And then for tensor networks, those of you who know about DMRG, so we got to bond dimension 65,000 without exploiting any structure. So that also for those who know about DMRG, you would appreciate that that's a lot. Okay. But nevertheless, part of the story is that the same week that we managed to get the largest DFT calculation ever accomplished, our team got canceled and we all lost our jobs, which is a sign of success. Luckily, we found other jobs short after. So as I was saying, the team that developed these strategies is no longer there. But we decided that nevertheless, we have very strong sense of humor. So we decided to write papers on the results, even after losing our jobs. And so we have a series of papers on the archive. Some of them have been published in PRX. I'm not sure. Well, if anybody is interested, all these papers are on the archive. Okay, providing details of what we managed to do with TPUs, and actually that's not just let's write a paper so we can get it out of the system, but most of what we did with TPUs can also be done nowadays with GPUs. So there is some merit to understanding what the new possibilities are. Computational, this had changed the computational landscape, and so those of you who are computationally inclined will appreciate maybe understanding that there is a gap between the type of hardware that you have access for your calculations and the type of hardware that would be available or that is available out there, which is usually only developed for machine learning, but actually you could be using also for this type of other calculations that you might be interested in. Okay, so that's the story I want to tell you. Let me start by, I moved from academia. I was in academia for over 20 years. I moved to industry 3 years ago, and people were asking, okay, how is it? How is it? Well, it's like that. I recruited a number of people from academia to continue research as usual, and the only difference is that I was tenured in academia and I lost my job after 2 years in industry. So yeah, that's a difference. So, but these guys, this Martin and Marcus and Adam were in my academic research group at Perimeter Institute. And so Ryan, Rui, and Johnny were PhD students in different places who joined us for a few months. And so we continued to operate as if we were in a physics department or physics chemistry department. Okay, so again, the story is the following. Over the last 5 to 10 years, there has been this arms race in industry to build the ever more powerful kind of hardware to accelerate and scale up machine learning workloads, right? So artificial intelligence, suddenly you have all these machine learning models. You want to train them, you want to extract it, or you want to have inference. And it turns out that if you use normal hardware, it's expensive. Machine learning would not scale nicely in normal hardware, but they saw that as an opportunity to simplify. You take your normal chip and you throw away everything that you don't need for machine learning. Okay, and you're left with a much simpler chip that then you can make run faster. You can specialize a bit more by adding additional units in your chip, and TPUs are an example of this, right? So TPUs are an example of ASIC, application-specific integrated circuits that were designed, again, exclusively for the purpose of accelerating and scaling up machine learning workloads, okay? TPUs are basically only useful for that. At least they were designed to only be useful for that. And what's a TPU? Well, I will give you a bit more details, but don't worry, I'm not an expert in any of the things I'm explaining today. So it won't get too technical, but you want to think of a TPU pod as being a unit, the largest configuration you can have, made of 2048 cores. And so you can imagine each core as being some natural unit of compute power, right? And we're going to be able to put 2000 of those together. And for those of you who know about performance, will be this TPU version 3. The entire pod with 2048 cores can operate at the 100+ petaflop scale, and it has high bandwidth memory, so memory that you can use very, very fast on the scale of 32 terabytes. Again, if you don't know what these numbers are, don't worry about it. I'll give you examples later on. But an example here that I could give you right now is if you are into quantum computing and you try to store the wave function of 40 qubits, 40 qubits, that's a lot. Don't try in your laptop again, but you can actually store 40 the wave function, full wave function of 40 qubits on these 32 terabytes of memory. Okay, that's one of the applications we consider. Okay, so the discussion today is based on TPU v3, the version 3 of TPUs. But in the meantime, there is already TPU v4 out there, and it turns out that instead of 2,000 cores, you have 8,000 cores, so a factor of 4 more. Instead of 100 petaflops, now it's more than 1 exaflop, so a factor of 10 plus. And the memory also went up by a factor of 4. So you can see that generation after generation, it's not like incremental improvement, right? Every generation, they multiply by 4 this thing, by 10 this other thing, and so on, right? So the race is still on. And this is only TPUs, then GPUs, and there are other chips out there that are competing closely. All right, so as I said, these chips were developed for machine learning only, but we wanted to understand the following. We wanted to understand whether by looking inside these chips and understanding what makes them useful for machine learning, whether we could take whatever computational building blocks we had there and repurpose those for more general scientific computing. And as I said, the answer, we managed to answer yes to this question. It is possible. And then we found applications to dense linear algebra, to the simulation of quantum computers, to quantum physics computations, and quantum chemistry and finance. Okay, so let's get started. And please ask questions. I mean, that's going to be really a light colloquium today. Let's get started with understanding what the TPU is, what makes the TPU special. Okay, I'm not going to give you a lot of details, just I want to comment on 2 things about TPUs. The first one is that TPUs are these chips that are good at multiplying matrices. What does it mean, or why are they good at multiplying matrices? Well, it turns out that the chip itself, which I denote here with just a square, so not a lot of details, as you can see, it contains a subunit called matrix multiply unit, or MXU, matrix multiply unit. Okay, as the name suggests, this subunit within the chip was designed to accelerate matrix multiplication. But actually, if you look at the picture, at the chip itself, it has the shape of a matrix. So what that means is that you can store a matrix, all the entries of your matrix. It's a matrix, it's 128 times 128 matrix in size. And you can store in each of the local registers, you can put your coefficients of your matrix. And then there will be some flow of information through that, and you will get your matrices multiplied, okay, natively. So instead of going element by element in your matrix and trying to have a loop over components, no. This multiplies matrices natively. That means 128 times 128 matrices get multiplied super fast, okay? It was designed to only do this. This unit can only do that, okay? Question? Is it vector by? Oh, no, the unit has this. Yeah, I think the question, correct me if I'm wrong, the question is whether it's multiplying row by row or vector by vector. It's a matrix multiplication. So it's matrix by matrix. So if you try to multiply vector times matrix, it's going to slow down. It doesn't know how to do that. So it's natively matrix times matrix. Yeah, thank you. Yeah, thank you. All right, so then each TPU core, right? It has this matrix multiply unit that is good at multiplying 128 times 128 size matrices, but it also has 16 gigabytes of high bandwidth memory. So that's the memory that sits very close to the processor, so that there is no that you can get data in and out very quick. Okay, so that's one core, and the result, the first property that we want to remember about TPUs is that as a result, it can multiply matrix. It can multiply two matrices very fast. Okay, very fast. I'm just going to say very fast, faster than what you are used. We'll see numbers later. So for those who know a bit more, we measured 10 teraflops of single precision matmuls on a single core. Okay, that's a concrete measure of how fast this is, but don't worry if that doesn't mean anything to you yet. So typical metrics that we would incorporate here, remember the small unit, the matrix multiply unit takes matrices of size 128 times 128, but because of the high bandwidth memory available, you can go to several thousand matrices on each core. So, okay, summary number one, TPUs are good at multiplying matrices. Single TPU core can multiply reasonably large matrices very fast. Now, point number two, instead of working with a single core, we're going to work with many cores, okay? And different cores will be connected directly through a fast intercore interconnect. So fast by some units, if you know about GPUs, maybe that's comparable to an NVLink. And if you don't know about GPUs, that's again okay. But the idea is that these units can perform very fast operations on each core, but then they can also talk to each other very fast. Okay. And then the basic TPU configuration is not just one core or two, it's 8 of those. And they always appear in a 2D grid. So they talk to nearest neighbor on a 2D grid with periodic boundary conditions. So that's like a torus. Okay, you put your cores in a 2D grid with toric boundary conditions. Very good. And you can have the basic configuration is 8 cores all the way to 2048 cores. And now at this point, what you have is that instead of using each core to make a matrix multiplication, you can distribute the matrix multiplications over all the cores. They talk to each other very fast, and so you have a distributed matmul executed extremely fast. Okay, this is not each core is very fast only, but actually they can operate collectively very fast. So that's the second aspect we want to remember about TPUs, that the different cores are connected directly with each other, so that distributed matrix multiplications can be implemented very fast. And so in particular, whether you use a single core or you use 2048 cores, when you look at how much each core is working, say to multiply two large matrices, you realize that in the distributed case, you have a bit of loss of accuracy of performance, in the sense that each core individually is operating at 93 to 95% of its capacity. Okay, so there is a little bit of efficiency lost in communicating data, but it's 5%, 8%. Yes. Sorry. Well, it's not. There is no loss of data. There is loss of efficiency, in the sense that each core, instead of only computing all the time, sometimes they need to wait a little bit for the data to arrive. Yeah, we don't lose the information. Yeah. But this 93 to 95% scale is very good. Okay. All right. So here's I've been postponing the discussion about what these numbers mean, and I want to have now a discussion of how powerful at multiplying matrices TPUs are. Okay, so this is a bit of a busy plot, but I'll explain it. I'll spend a minute explaining it. So this plot characterizes performance and multiplying two matrices. Okay, now the x-axis here, the horizontal axis, has an n in it that is 1,000 all the way to 1,000,000. That's the linear size of your matrix. So if you read 1,000 here, that means we're multiplying matrices which are 1,000 times 1,000 elements. So you could do this one with your laptop. Okay. Maybe this one 10,000 times 10,000. Don't try 100,000 times 100,000 or 1,000,000 times 1,000,000. Okay, this is definitely beyond reach of small compute clusters. Okay. All right. So what we did, and then the vertical axis is how fast the calculation is taking place in the sense of the teraflops, how many floating point operations are being executed per second. Okay, so when we started this, we didn't know what was going to happen. Okay, but we needed that as the building block for everything else that we did. And so it was important for us to understand, not by reading specs on how TPUs work, but actually by implementing these calculations to see how good these machines are at multiplying matrices. And so what we did is first, we wanted some CPU reference. We wanted to use some CPU machine, right? The regular CPU, so that we would be able to compare performance with the TPUs. And when we did that, we went to Google Cloud and we looked for the machine in Google Cloud, the CPU machine that had the largest memory, so that we could store all these big matrices. Otherwise, we could not even start the game. And so there was a machine called UltraMem that happened to have 208 CPU cores. And that's the machine that we use to multiply large matrices on CPUs. And so and this black curve here tells you how the CPUs are performing. And you realize that as you consider larger and larger matrices, the CPUs are crunching more and more numbers, okay, until they saturate to some number. And after that, we stopped because it was really very expensive to run these machines for multiplying matrices that nobody cared about, right? So we saw saturation that was consistent with the spec. So we thought, okay, we've tested the CPUs. So this is, CPU is 208 CPUs. And somewhere at maybe 20,000 or multiplying 20,000 or 30,000 matrices of linear size 30,000, that's where you have all the CPUs working at full speed. Okay. Now, a single GPU, 800, would perform at twice this rate. Okay. So a single GPU, one GPU is better. It would be better already. It would be better than 208 CPUs. So GPUs are spectacular. Now, instead of GPUs, we wanted to test TPUs. And remember, the simplest TPU configuration consisted of 8 cores, 8 here. So in blue, we have the performance of 8 TPUs and multiplying these matrices. And remember, this is the size of the matrices. So we could go all the way to a certain size. And after that, we would not see improvement anymore. Also, we would be saturating the high bandwidth memory. So we could really not multiply larger matrices. But then instead of using 8 TPUs, we could use 32 in yellow, okay? And we could get to larger, you see a significant improvement in performance, and also we can go to larger sizes. And we can do that for 128 cores or 512 cores, all the way to 2048 cores. And by the time we get to 2048 cores, and remember, these are machines that are out there available to anyone on Google Cloud. So you literally can access those instead of trying to find time on your favorite supercomputer. Say you have friends who can connect you to the right person and end up in a national lab. You apply for a grant proposal, and then they eventually decide no, they don't like your project, or yes, they like your project, and then they allocate time, blah blah blah, right? 3 months down the road. No, this is, you need a credit card. That is a detail, right? But you need a credit card and account, in this case in Google Cloud, but I'm sure there are other offerings out there, and you have access to this machine, okay? And this machine was able to multiply these large matrices 2,000 times faster than with the CPUs, okay? 2,000 times faster, it's 3 orders of magnitude. That's not something you can ignore. Okay? But you could argue, okay, yeah, 2,000 times faster, maybe it's 4,000 times more expensive. So why don't I just wait some time and I'll get it done? Actually, when you look at the time of using this machine, the total time of renting the machines for the overall calculation, it turns out that TPUs were 50 times cheaper than the CPUs. Okay, so that's, these numbers can oscillate a little bit depending on what deal you get, right? But it gives you an order of magnitude that if you build a machine that is only good at multiplying matrices, maybe it's worth using, right? It's going to be much faster and cheaper. Question? So these are the same generation TPUs. We are just putting more together. And we use the largest configuration available. And I don't know why they stopped at that size. The next generation goes faster and has factor 4 more cores. So I don't know what the limit is, right? This is a snapshot of technology 1 year ago. And in the meantime, this has been increased by a lot. I don't know what the ultimate limits are going to be. To the extent that Moore's law is a law, yeah, I don't know. So what they did was they simplified, they reduced the coefficient in front of the n-cube scaling, right? They still have to put all these components in a chip. I'm guessing the answer is it's limited by Moore's law. They also talk about, instead of the amount of compute, this tends to be limited by how fast you can bring the data in the right place. Yeah. All right. So there we have it. We have a machine that multiplies very large matrices, so unprecedentedly large matrices, extremely fast. And that was a year ago. And in the meantime, NVIDIA GPUs, right? They say, "Ooh, let's do the same." And actually, that's a busy plot. I don't want to spend too much time here. But nowadays, you can do that and even more with GPUs. Okay, the connectivity between GPU cores has improved a lot over the last year in such a way that you could multiply even larger matrices possibly faster. And I'm not here to advertise NVIDIA or Google or anything. I just want you to know that the technology is there. I'm just going to go run. I notice I'm going a bit slowly today, so I'm just, if you have questions, I'm happy to answer them later. Okay, let me move on. So we can multiply matrices. So what, right? You learn to multiply matrices at primary school, probably. So we actually managed to multiply mostly 2 types of matrices, and all the applications we found afterwards were coming from just these 2 types. The first type is you take a square matrix, like 1,000,000 times 1,000,000, right? You take 2 of those and you multiply them, you get a square matrix of the same type. Another type of thing you can do is you can get a small matrix multiplied by what they call them fat one, and you get another fat matrix. So here was 1,000,000 times 1,000,000. This is 100 times, I don't know these numbers anymore, 10 billion or something. Okay. Then the number of coefficients here and here are the same, just that you are organizing it in a different way. Okay. So what can we do with the square matrices? It turns out that apart from obviously dense linear algebra things, like once you can multiply matrices fast, and maybe you can also add them together fast, you can compute matrix polynomials. And before you notice, you can do a lot of things with matrix polynomials. There are so-called Newton-Schulz iterations. It turns out that there is a lot of literature out there, which was kind of marginal, because that's not the way you would usually implement your linear algebra. There are faster ways of doing that on a CPU. But if all you can do is matrix multiplications and matrix additions, then it turns out that this is the way to go. Just build matrix polynomials. And apparently, there are lots of things you can do with just matrix polynomials. It's not what you usually learn, because that's not how CPUs work. Okay, but TPUs would, with TPUs, you would need to use these strategies. And then you can have also matrix decompositions, like a singular value decomposition or an eigenvalue decomposition and so on. Now, once you have this dense linear algebra, it turns out that you look at quantum chemistry, and lots of quantum chemistry algorithms can be rewritten as matrix-matrix multiplications and composite instructions based on matrix-matrix multiplications. So with this square matrix multiplication, we managed to implement a number of algorithms that are relevant to quantum chemistry and also in finance. This one here instead, you can imagine if you are into quantum computing, that if you want to multiply your massively large, you have the wave function of n qubits, and this is a 2 to the n component vector. And now you want to upgrade your wave function under the action of a local gate acting on 2 qubits. It turns out that you can reshape this into a matrix multiplication of this type, where this is the 2 qubit gate, and this is your wave function that has been reshaped properly. Okay? So it turns out that that's what it takes to simulate quantum computers. But also, once you do that, you can also do quantum many-body physics, in the sense of they give you the Hamiltonian of a spin chain or a spin lattice, and you want to find the ground state of that Hamiltonian. All it takes, again, is to multiply matrices in this way. Okay, so if they close you in a room and say you cannot go for dinner until you find applications for matrix multiplication, then this is what happens. You realize that you can rewrite lots of things you were doing until that day in terms of matrix multiplication. Okay. And how do you distribute this on TPUs? Remember, we have a multi-core TPU setup. Well, it turns out that the distribution of this is trivial. You just break your matrices into pieces and send different pieces to different TPUs, TPU cores. And remember, the cores are organized as a 2D grid. So it's a match with breaking the matrix into a 2D grid as well. And there are some details, and I don't want to say that it's trivial, but it's surprisingly simple. And for those of you who are interested, we use the Giufre library, which is a Python-based library. And there are a number of details, like the just-in-time compiler that maps from Python to high-level operations, and then there is this XLA compiler that translates from high-level operations to low-level operations, and lots of details that I'm happy to discuss, or at least give you some guide if you are interested, but we can talk later. And then there are a number of constraints. I mean, TPUs really only know how to multiply 128 times 128 matrices, so you need to be aware of that. If you go there and try to multiply 10 times 10 metrics, so, you take two matrices which are 10 times 10, and you try to multiply them. Okay, this machine doesn't know how to do that, except that it will pad with zeros all the way to 128 times 128 matrix, and then it will multiply a lot of zeros for you, right? Really, really fast. But it's a waste of time. So it takes as long. A matrix multiplication should scale as m to the cube, n cube. Okay, but all the way to 128 size. So for sizes smaller than 128 times 128, you pay a flat fee. Okay, it doesn't matter the size of the matrix; it's always the same cost until you hit 128, and then it starts going up. Okay, so you don't want to end up multiplying small matrices with the TPU because you're wasting time and money. All right, and yeah, I see. Very good. So TPUs for dense linear algebra. So I already covered like 20% of the presentation. It's good. No, I'm happy to keep it concise today. So the next question is, what can we do, right? What can we do with multiplying matrices? And so I started hinting at that. But maybe if any of you ends up thinking about this and wants to implement it, you may want to know that indeed, once you multiply matrices and maybe add them together, you can do a number of things. And a typical operation that we've been doing a lot was a polar decomposition. What's a polar decomposition? Given a matrix M, a polar decomposition of matrix M is a pair of matrices U, unitary matrix, and rho, which is a positive semi-definite matrix, that if you multiply together, give rise to the input matrix M. Okay, so polar decomposition, that may sound like polar decomposition of a complex number. You take a complex number and you decompose it as a complex space times a non-negative number. That's the same, but with matrices. Okay, instead of a complex space, now you have a unitary matrix, and instead of a non-negative number, you have a non-negative or positive semi-definite matrix. Okay, so it turns out that just by multiplying matrices number of times, you can get there. You can have a polar decomposition. And similarly, if you can have a polar decomposition, you can have the sign function, which takes your matrix and replaces the eigenvalues with +1s or -1s. You never eigenvalue decompose the matrix. Okay, you just have the matrix, you multiply it many times in some weird way, and the resulting matrix is the same as if you had replaced all the eigenvalues that are positive by a +1 and all the eigenvalues that are negative with a -1. And similarly, you can take the inverse square root. And you would think these operations are completely unrelated, but actually they work with exactly the same underlying algorithm, which is this Schulz-Newton iteration. Okay, and then eventually we can do singular value decompositions and whatnot. And these two here is what all that we needed for density functional theories in quantum chemistry. All right, so these are more details, but I don't think we need to go much into those about what Newton-Schulz iteration looks like for the polar decomposition. Basically, you give me the input matrix, okay, and all I have to do with this input matrix N is I have to square it, take 3 times identity minus this square, and multiply the result by the matrix again, divided by 1/2, or divided by 2. Okay, and I have to do this, and that's the input for the next iteration. And I have to do this like 20 times, and after that I get the polar decomposition. Okay? It's deterministic. You don't have to worry about conditional, nothing. It's you just apply this iteration 20 times, 30 depending on how much accuracy you want, and that gives you the polar decomposition. And this, as I mentioned, the sign function and the inverse square root are identical. It's contained within here. It's complicated, but it's already in here. Okay, and if you want to do something more complicated, like a full singular value decomposition of a matrix, then it's a sequence of increasingly complex combinations of matrix multiplications. But again, matrix multiplication followed by a matrix multiplication, followed by a matrix multiplication. All right, and so we tested that. And if you want details, we have the details here. This got published, and I forgot to update the reference. But you have matrix multiplication. Now this is time to solution versus the linear size of the matrix. And you have that as you put more TPUs, you get better performance. You can get to larger systems, larger matrices. Now this cost typically matrix multiplication, we know it's n cubed. And so this is log scale. N is here. This is the time. And so these straight lines that you see here symptotically, they are already n cubed. Now the trick with hardware like this that you can scale up is that every time you want to increase the size of the matrix, which would lead to, if we double the size of the matrix, we should have that the cost is 8 times, right? The time should increase by a factor 8. But what we're going to do is every time you want to double the size of the matrix, we're going to throw in 4 times more cores, right? So instead of going from, instead of having to wait 8 times, now we throw in 4 times more cores. And so we're going to have to only wait twice as much. And so what I'm saying here is that because this machine scales so well, by throwing in more cores, as we increase the size of the matrices, we go from cubic scaling, so n to the 3rd power, to n scaling, right? If you just follow this sequence of points, you realize that you're solving an n cubed problem in time that it's only n. Of course, you are throwing in more hardware, right? But it's like it scales so nicely that you can just do that. Okay. And we did that for a QR decomposition, which is another type of matrix decomposition for solving linear systems, and also the polar decomposition I just discussed. And in all cases, you see this linear scaling for problems that should scale as n cubed, but thanks to being able to use more and more cores, we can lower the exponent. All right, so let me check again. Right, so let's see. Applications of that, more details on applications of that, and I think I'm just gonna chat over those quickly. We decided to apply this to quantum chemistry. Maybe I realized this is not quite the right department. This is physics colloquium. But I can tell you, I was a physicist for most of my career, and I would always thought that, you know, chemists are those who couldn't make it to physics, right? It's like, okay, I know that's not politically correct, but this is a physics department. Anyway, in the process of looking for applications of TPUs, I realized how amazing chemistry is. You know, we are used to thinking of a spin chain. Oh yeah, I'm gonna solve the Ising model, you know, for the 20th time. Maybe there is an application this time to industry. But actually, in quantum chemistry, this is really amazing. Everything they do, it's like real-time real world application. Okay, and this is about, you know, from nucleic acids to studying protein ligand complexes, enzymes, and so on, to crystal structure prediction, to create, you know, how you create medicines that will deliver what they need to, catalysts, nanochips, solar cells, batteries, all these well, that's more like material science, but you have all these applications. It's just fascinating, and you know, it took me 20 years to realize. And in quantum chemistry deals mostly with chemistry that needs a quantum level description, right? So depending on the scale at which you are operating, maybe a classical description is all you need, but there are problems when you go to sufficiently small sizes or phenomena that involve, you know, the electronic structure of a molecule, where you really need a quantum treatment. And it turns out that quantum treatments for chemistry, there are many possibilities from density functional theory. This is supposed to list a few methods in quantum chemistry. From density functional theory, where the cost scales as the third power of the number of orbitals, which, you know, there is something called the number of orbitals. So you can have cost as the third power all the way to exponential in the number of orbitals. The idea is there is a hierarchy of methods that will give you more and more accuracy, but that are more and more expensive, right, in quantum chemistry. And what's fascinating is that if you look at the details, there is a lot of, you know, lot of things you may need to learn. But when you look at the bottleneck of each method, you realize it's a massive matrix multiplication. Okay, that's the computational bottleneck on all these methods. Okay, and we had a larger scale matrix multiplier. So we decided to start exploring applications on all these methods. And I'm not going to have time to tell you about the usual story about what orbitals are, but the number of orbitals that you decide to use to describe a molecule will define the complexity of the problem, at least formally. And the idea is that, for instance, in density functional theory, which is the algorithm that we implemented with TPUs, there are two pieces to the algorithm. One is to prepare a Hamiltonian. You are familiar with Hamiltonians. It's going to be an n times n matrix that has to do with some effective free fermion problem that you are trying to solve. So you need to prepare this n times n matrix, and we're just going to use CPUs for that, normal computational resources. And then you need to do an n cube operation on this Hamiltonian, okay? And that's where we're going to use the TPUs. The idea is you need to prepare a Hamiltonian, solve it in the sense of applying an n cube operation. Then with the solution, you go back and redefine or reset your Hamiltonian to something else, and then you solve it again, and you go back and forth. Okay, there is something called the DFT iteration, which consists of every problem you are formulating here. It's a free fermion problem, okay, that you need to solve, and then you use the solution to effectively define a new a free Fermion problem, and you want to do that until convergence. And so the idea is that we didn't need to reinvent the CPU part. This was not the bottleneck, right? We could tackle the bottleneck with this scales as n squared, whereas this is n cubed, n being the number of orbitals. And for say n equal to 1,000 or 10,000, that clearly dominates over this part. And so we focused on rewriting all the steps that go in here for TPUs with matrix multiplication. And after doing that, well, you know, we found this again scaling that it's n cubed turned into n, and so on. And we applied to some systems, and you can have the paper here. And the net result is that we managed to have the largest DFT calculation ever performed with 250,000 orbitals. And we actually only used a quarter of the full pot. So we did not even use a full pot. Okay, we used just a quarter, 112 cores. We could have gone bigger, but as I said, our effort got canceled that week, so we couldn't go bigger in the end. Okay, so that story, then we've applied this also to material science and nanotechnology, to a number of systems. We've been doing DFT, density functional theory, this quantum calculation, right? This quantum chemistry. The calculation suddenly, because we can go to very large system sizes, we can deal with the full protein, including the water around the protein. And this is something that was not possible before. Okay, and I'm running out of time, but you get the idea, right? That there is this hardware out there which is available. You choose your favorite application. And if your favorite application is based on matrix, or the bottleneck is a big matrix multiplication, or as in this second example, on DMRG, the bottleneck is some tensor network contraction, it turns out that TPUs can accelerate that. And when I say TPUs, I mean also GPUs nowadays and other ASICs, similar ASICs. And all you need to know is that this is available, and it takes some effort, but the reward is pretty impressive. You can go to say 2 or 3 orders of magnitude bigger than you are used to. All right, and I'm going to stop there. And thank you very much. The end of the question again, sorry. The one that we performed? Oh, that's a good question. So I don't know, a few $1,000s. Yeah, on the order of a few $1,000s. So you don't want to repeat it many times. Yes. The way we implement tensor network algorithms. Oh, sorry. Oh, the question, right. So Ehud is asking, in tensor network algorithms, I claim that we just multiply matrices, but it's true that we have to contract 2 tensors. It's not matrix multiplication, it's tensor multiplication. So the way we actually multiply 2 tensors together, even on CPUs, typically is by reshaping the tensors into matrices and then applying a matrix multiplication. So even though it looks like it's something else, at the end of the day, we're typically using matrix multiplication for most or all of our tensor network contractions. So it's the same thing. You can take this as generically, we can speed up all tensor network algorithms. On this example that I didn't have time to go through is DMRG with one dimension 65,000, is it? I don't remember. Yeah, I think it's 65,000 somewhere. Yeah, so, and without exploiting any symmetry. So natural dimension that you would use without exploiting symmetries here would be, say, 1,000, right? And now we go 65, a factor of 65 more. And again, we stopped this because we were asked to stop, not because we saw the end of the capabilities. So we believe we could go to DMRG with one dimension, 500,000, for instance. That's right. That's right. Covariant, contravariant. Yeah, no, for me, for what I meant by tensor, indeed, it's a larger order array of coefficients. So what are the options? What could you get? What are the options? Well, they don't sell TPUs. So. Oh, NVIDIA maybe. I don't know. Well, yeah, I shouldn't be recommending. So it depends on what your bottleneck in your calculations are. If the problem was that you couldn't fit your problems in the GPU memory, then you should be looking at a node where several GPUs are connected with each other with NVLinks, for instance. Yeah. Yeah. So I was, in my head, reality doesn't count, right? So I thought about what I would do next indeed. And I was going to go for tensor networks 2.0, right? Where you don't need to improve the algorithms. You just go ahead and get to unprecedentedly large one dimensions, say in 1D or 2D, say PEVs, meta, maybe 3 dimensions. And I thought, I still think that just with the next generation of hardware, where you can go get to much larger one dimensions, we would find out how powerful these methods really are, right? Because in principle, with tensor networks, the limiting factor is not the system size anymore, but the amount of entanglement you can account for with your answers or your one dimension, right? So if suddenly you go to PEPs with one dimension 50, maybe you start solving problems systematically with that. Maybe not, right? But I believe that a larger class of problems could be solved with the same type of tensor networks that we have today. This was TPU version 3. Yeah. Larger and faster. TPUs. I have no idea. I don't. Yeah, GPUs can scale in the same way, even bigger. this meaning having access. Yeah, I mean, Google already offers access to TPUs through collabs. So if you know about collab, right? So it's like a IPython or Python notebook that runs online, and you have a choice of runtime, and you can use, I think, GPU or TPU or CPU. So these things happen, right? The Google understands the value of offering some resources for free, and so it could happen with TPUs at a larger scale, not single TPU done, not the small configuration, but the large one. So yeah, it's possible. They are in the cloud. In the cloud. The basic quantum mechanics of TPUs. But TPUs are classical hardware. There's no quantum. Oh, for the quantum applications? So the quantum applications are, you talked, I mean, you're in the right place, right? Many people here know about simulation of quantum systems. All I'm saying is that typical algorithms, say tensor network algorithms that are being used for simulating quantum systems, you could use a TPU to accelerate those. But you really are in the right physics department to ask about quantum. Yeah. Oh, no. That's definitely, that happened afterwards. I mean, but apart from that, the GPU technology, the connectivity is there, but it's not yet accessible by everyone. I know the hardware is there, it exists. When I talk to people at NVIDIA, they tell me what's the latest, but it's not offered online like through cloud or anything. As far as I know, I mean, this thing changed so fast. Right? But, yeah. Finance was really amazing. I was talking to these companies in finance, and they would not even tell me what the problem was that they wanted me to solve. So they would only allow me to say, no, you need to do this and that, but we're not telling you what the input data is, or yeah, they were super careful. We found a solution for them, but we still don't know what problem to solve. There is no paper. There is no paper on that one. Yeah, I wouldn't know what to write. Yeah. Yeah, my approach is the naive approach of write the full wave function, and that's going to take 2 to the n coefficients, and then multiply it by Hamiltonian terms or whatever you need to do in order to, say, evolve according to the Schrodinger equation or an Euclidean time evolution, or apply Langtos or some way of finding the ground state. So my approach is the most naive approach. And the only thing I'm saying is this most naive approach, it's very inefficient. But if you have a machine that can perform it very fast, we don't beat exponential. This is still exponential, but the coefficient, the cost is exponential in n, but the constant multiplying exponential in n just got reduced by a factor of 1,000. That's all I'm saying. With the TPU v3 pod, we were doing 40 qubits. With the TPU before we could have done 44 qubits. But this is full wave function simulation. It's not like any tricks of storing part in memory and part. No. This is just put the full wave function there, right? 2 to the n coefficients. Yeah. So we did 40 qubits. We could be doing now 32. I think with NVIDIA 45. Yeah. There was a factor 4 in memory, right? No, 2 qubits is a factor 4. Oh, what? So we had from V3 to V4, I think I said that the memory was up by a factor 4, and that would be adding 2 qubits. Sorry? I don't know. What's the world record of? Yeah, exactly. The answer is I don't know what the world record is. But people working in exact renormalization for the longest time, they are very, very smart people who understand how to exploit any symmetries. Internal symmetries, say your spin system is Z2 symmetric or U1 symmetric. Space symmetries, like you are studying a square lattice that has 90-degree rotation symmetry or reflection symmetry or translation symmetry. And those things end up not. So when you try to exploit all the symmetries, which you could do, then you don't end up with matrix multiplication. Okay? Whereas TPUs is the brute force approach where you say, I have 2 very large matrices, boom, and multiply it. Right? There are smarter ways of doing things quite often. But TPUs are, you don't think about TPUs as a very smart piece of hardware. It's a very strong piece of hardware. You cannot think. So big matrices, dense matrices, brute force multiplication. Okay, thank you.